All right, so that is our basic requirement. What does it say though about the material? To understand what more it says, we go back to our, we now take steps that are going to be very similar to what we did in the context of material frame invariance, except we're doing something different, right? We're talking about material symmetry, right? We're talking about material invariance itself. Okay, so we do use the polar decomposition, but we used the other polar decomposition than we used previously. In particular, we recall the left polar decomposition. Okay, and that was that F can always be written as VR, right? Correct, where V is a stretch tensor, it's a symmetric tensor, it's positive definite. Okay, and R is a handedness preserving member of SO3. Okay, R is a rotation that preserves handedness. Okay, all right, so this is the left stretch tensor. Okay, and this is the rotation tensor. Okay, so material isotropy tells us that our function psi should be such that psi of f equals psi of f q transpose for all q correct? But on the right hand side, we are now going to invoke our left polar decomposition. Okay? Now we do the same sort of mathematical, carry out the same mathematical argument as we invoked to make our case for material frame invariance, right? We say that, all right, you go ahead, we say that, okay, you go ahead, pick the point and the time at which you want to impose this argument, okay? And then what we observe is that, well, since we have the left polar decomposition, right, in this form, correct, in this form, and since this must hold for all q, right, this must also hold, okay, so consider in particular q, which is equal to r at the point of interest and the time of interest, right? Suppose that q is such that at the time of interest, it coincides with the rotation tensor at the point for which you want to apply these arguments, right? And we know that that particular q is also included among all those that must satisfy this relation. Okay? Since it is included, what we see that is that psi function of f must depend upon psi of v only. Okay? Right? And so from this, just as we did in the case of material frame invariance, we conclude that for a material to be isotropic, psi has to be such that its dependence upon the deformation gradient is only through the left stretch tensor. Right? Okay, but if psi depends upon f only through v, we also have but we also recall the left Cauchy-Green tensor. Okay, we introduced this a long time ago when we studied polar decompositions. We defined this tensor as little b, which is F transpose. Okay? Looks very much like our right Cauchy-Green tensor, except that the position of F and F transpose have been reversed. Positions of F and F transpose have been reversed in that product. Okay? What we showed back then is that V square equals B. Okay? So, since material isotropy implies that psi as a function of F should be a function of V, we observe that, oh, but it can also be a function of B. Okay? Right? For isotropy only. However, frame invariance still must hold. Okay, because frame invariance is a fundamental physical requirement. Material isotropy is a choice for the material that we are working with. Okay, so, but frame invariance always holds. Okay, and here I'll state parenthetically that material isotropy is a particular choice for material response. Okay? Put differently, everything has to be frame invariant. All psi's have to be frame invariant. Not all psi's have to be isotropic. If you don't have an isotropic material, the arguments we are making don't hold for isotropy. Simple as that. Right? Certain materials do indeed care how you orient them before presenting them to a deformation. Right? So this is the difference here. Frame invariance always holds. Okay? So what does frame invariance say? Remember what frame invariance was. It was this picture. Omega naught going to omega t being subject to a rigid body motion. Okay? This is frame invariance. Okay? This was F. That was F plus. Okay? And the relation, if this is phi, that is phi plus, which is C plus Q little x. Okay? Remember all this. Okay? And in this setting, we see that F plus equals QF. Okay? All right? Things look different for frame invariance. This condition must always hold. Okay? All right, if that is the case, what happens with B plus? Since frame invariance must always hold, B plus, which is F plus transpose, is Q F transpose Q transpose. Since this is B, we have that B plus is Q, B, Q transpose. So, the fundamental requirement of material frame invariance always holds, and it says that it says that, well, all right, you have an isotropic material. You have discovered that you indeed can write its strain energy function as that. But frame invariance, which is actually a more important requirement, which must always hold, or we just go home and say we don't know how to model materials. Okay? This must always hold. So it is such that this condition must hold for all Q. Okay? All right? The reason this shows up is that unlike what happens with our right Cauchy-Green tensor, which did not care how we were rotating the current configuration, okay? This deformation tensor does care, right? B does care how we're deforming the reference, what we're doing with the current configuration, okay? And so we observe that B plus is indeed related to B in this fashion, okay? Recall that C is F transpose F, and therefore if you wanted to calculate a C plus, you would see that you would observe that you got F transpose, Q transpose, QF, which was the same as C. Okay, because the right Cauchy-Green tensor is defined on the reference configuration. This is where C lives. Okay, so it does not observe what we are doing with the current configuration in terms of doing any. When we apply rigid motions on the current configuration, those are not observed by C. Okay, these types of motions are not observed by C. Sorry. Okay, these types of motions are not observed by C. B lives here. It does see that motion, that rigid body motion on the current configuration. Okay, and so when we apply frame invariance, we see that we have to further satisfy this requirement. Okay, but now that requirement must hold for all tensors Q. Okay. What we conclude from here is that psi can depend upon B, but it can depend upon only certain very special functions of B. Right? What are those functions of B? Those are the functions of B, the principal invariants of B. Okay? All right? Those principal invariants are the trace, okay? The second principal invariant is the square of the trace of B minus the trace of B square. And the third principal invariant is the determinant of B. Okay? All right. So if you have an isotropic material, okay, because it must always be frame invariant and every strain energy function has to be frame invariant, we conclude that for an isotropic material, we must indeed have psi depending upon the principal invariance of B. Okay, so furthermore, we could say that, yeah, you have psi equals psi tilde of B, which could now be a psi. I think I'm running out of ways to decorate psi. There are hats, there are bars, there are tildes. Let's just put 2 tildes. Okay, it must be a function of the principal invariance of B. Okay, but now here's an interesting fact. How are the principal invariants of B related to the principal invariance of C? What is its relation? They're the same. Okay? All right? So, this is fully equivalent. Okay? So, we could have reached the same conclusion by taking our strain energy function, requiring that it be frame invariant. Okay? So, we could have started out with psi, function of f. We could have first invoked frame invariance, which would have given us this. Correct? If then we imposed the further material modeling choice to say that this particular material is also isotropic, okay, right, we would have concluded that for the case of isotropy only, we would have said that, oh, it has to be a function of C. What if in particular I were to make it a function of the principal invariance of C? Then we would have gone from a material that was just frame invariant in the middle to a material which is isotropic. Okay? So this requirement comes from frame invariance. Okay? And this last requirement comes from isotropy. Okay? Okay. However, right, if we say that, if we were to start out and at the outset say that our material is some function of psi of B, right, it has this form, what we are wedded into is that this material is isotropic. Okay, we're straight away talking only of an isotropic material if ever we write this. Okay? Since we also know from here that it has to be frame invariant, okay? Okay, it's isotropic, must also be frame invariant. Okay, and this says that, okay, it has to then be a function of, we say, oh yeah, it's a function of B, but really the only sort of function of B I'm allowed to have is that one, which of course is dependent also, which has the same dependence upon the principal invariance of C, because the principal invariance of C and B are the same. So, yet another way to look at it. This is a fundamentally unsound model for a fiber reinforced composite or a crystal, right? All right, so if you're trying to model a material that is a single crystal and you make it a function of B, wrong, dead wrong, can't work. Okay? Because you're not then saying that your single crystal is isotropic, which is just not right. Okay, same thing for a fiber reinforced composite. It cannot be a function only of B. When we write something as a function of C, okay, like we were doing all along until we happened upon today, we left ourselves open to the possibility of having a material. It is frame invariant, of course, okay, and that's good. But as long as we leave it as a general function of C, or of course of E, right? It's frame invariant, which is good, but it is not necessarily isotropic. If you want to model crystals, this is good. You have to maintain this generality. We have to maintain that generality. Okay? So this thing is frame invariant, not necessarily isotropic. If we want to further make it isotropic, that is what we have to say. We have to say it's a very special function of C, or of course a very special function of E, because we can rewrite C in terms of E and all that stuff, right? And then rewrite the invariance of C in terms of the invariance of E, right? We can do all that, okay? But that's a very special type of material. It's isotropic. For general materials, which are single crystals or more, right? And anything that actually reflects crystallographic structure, right? Or fiber reinforced composites. Right? All of these can be functions of C or E. Okay? General functions of C or E. And then, of course, the question of how good a model it is for the particular composite or the particular crystal we are trying to model depends upon how well we pick these functions of E or C. Okay? All right, so we better end this section here, this segment here.